Okay, we're going to talk about the material from Lecture 8. Lecture 8. As always, watching these videos is not a substitute for reading the book or notes. This is just in hope to help you with that. Okay, remember me talking about experiments at some point, and you do an experiment, you get a result. The result is called an outcome of the experiment. Right? So if you flip a coin, the possible outcomes are heads and tails. And we don't admit that landing on edge is a possible outcome for a coin. You roll a die, the possible outcomes are the numbers 1, 2, 3, 4, 5, 6, and so on. We need a few more words around that. First, an event is a set of outcomes. It could be all the outcomes possible. It could contain 1, 2, 3, 4, 5, and 6, for example, for a single die. It could be some of them. It usually is some of them. It can even be none of them. Even though we insist that an experiment have an outcome, the experiment cannot end up with no outcome, we allow the impossible event. The impossible event is the empty set, right? That contains no outcomes. You can write it that way, or you can write it as a crossed out zero thing. They're pretty much the same thing. It doesn't matter which way you write it. You need to be able to read it both ways. Besides the impossible event, there's another very special event called the sample space. For historical reasons, the sample space is the set of all possible outcomes. So, for example, if you were to roll one die, and of course dice are six-sided fair dice in this course, unless something tells you otherwise. Right? If you roll one die, then the sample space, the set of all possible outcomes, is just 1, 2, 3, 4, 5, 6. Some possible events. We're not going to list them all, but certainly the empty set is one of them. That's a possible event. Or it's the impossible event, but that's one of the events you could list. How about the event containing just the number 2? That's the event that when you roll the die, you get a 2. Right? And here's another one, 2, 4, and 6. That's the event you get an even number. We say that an event occurs if, when you actually perform the experiment, the outcome of the experiment is in the event. So suppose the event E is, this is for the experiment of rolling one die. E is the event 2, 4, and 6. Then if you roll the die and you actually get a 2, 4, or 6, then this event has occurred. If the event were, let's say, F, the event 1, 3, 5, if you roll the die and you get a 2, 4, or 6, this event occurred, but this one did not because the outcome is not in there. Okay, let me say a few words. You've seen these before, but just a few words then about Venn diagrams. Right? When you use Venn diagrams to represent probability things, you usually use a rectangle to represent the whole sample space, right? And then all the points in that rectangle, right? Whether there are finitely many or infinitely many or whatever, all those points are outcomes, and the sample space contains them all. We use circles, usually, or something as close as I can draw to a circle, to represent events, and events contain outcomes. These outcomes here are in this event, which might be labeled E. Right? E contains this outcome and this one, but it certainly does not contain that one, and so on. The usual thing, if you mean, here's an example where you have two events, E and F. If you mean to talk about all the outcomes that are in both E and F, you can just shade that region. This is something you must be used to from previous courses. We often use them to talk about probabilities, talk about events, outcomes, and so on. Okay, let's try to define probability. This is written out in the book, but the probability of an event E, this is a number between 0 and 1. Right? It can be 0, it can be 1, it can be any real number in between. When an event has probability close to 0, that means it is very unlikely to happen. If the event has probability very close to 1, that means it is very likely to happen. If the event has probability 0, that means it can't happen. It's the impossible event. That's the only event with probability 0. And if the event has probability 1, that means that it must happen. Now, probability, mathematical probability, just has to do with assigning numbers that are between 0 and 1 to events, subsets of some sample space. So you have a subset of a sample space, you assign it a number, and so on. But that doesn't lead to anywhere really productive. What you need to do is you need to establish some rules for assigning those numbers so that when you calculate probabilities mathematically, they turn out to be the actual probabilities of events occurring in the physical world if your sample space models an actual experiment. And the rules we accept are that the probability of the empty set is 0. That's what I was saying about 0 being the probability of the impossible event. Also, the probability of the sample space, the whole sample space, is 1. And here's one that's a little less completely obvious. The probability of the event containing outcomes X and Y can be calculated by finding the probability of the event containing only X and adding the probability of the event containing only Y. We probably wouldn't put in all these braces and so on. Probably I would really write that something like this. P of X plus P of Y. Now these X and Y are really outcomes, but we don't really want to write all those curly braces, so we just pretend that they're there. Now these rules all together, but in particular this rule and this one, right, together have a certain consequence. Suppose you have a sample space S. Right, this is a sample space, so all possible outcomes of an experiment, right? And it has n outcomes in it. Right? So it's a finite sample space, and it has exactly n outcomes for some number n. And all outcomes are equally likely. That happens fairly often. Right? Think of tossing a coin. Heads and tails are equally likely, or rolling a die, or rolling 2 dice, right? Or drawing a card out of a deck. Right? Any card is just as likely as any other to be drawn out, and so all the outcomes are equally likely. Lots of things are that way. In this case, what's the probability of the sample space? Oops, I meant to write that. Probability of the sample space. That's going to be the probability of, well, let's just write them as this. X1 plus probability of X2 plus, and so forth. If I add up the probabilities of all the outcomes, all n of the outcomes, I have to get the probability of the sample space. Well, I already know from one of my rules that the probability of the sample space is 1. And because all these outcomes are equally likely, they all have to be exactly the same thing. So what are n numbers that are all exactly the same that add up to 1? Right? They each have to be 1 over n. There's nothing else they could be. So if you have a sample space with n outcomes, all of which are equally likely, then the probability of any one of them is just 1 over n. So for example, if you roll one fair die, so that all the outcomes are equally likely, then the probability of getting any one of those outcomes is 1 out of 6, because there are 6 possible outcomes, 6 outcomes in the sample space. All right. We divide probability into kind of 2 categories, called theoretical probability and empirical probability. Theoretical probability, that's when you're talking about mathematics. You simply have a sample space and subsets of that sample space, events, and you assign numbers to the events, numbers between 0 and 1, numbers that satisfy those rules we gave, and you end up with some kind of probability system in which you can calculate things. The other type of probability is called empirical probability. Empirical means of the world, and that is when you're talking about probabilities from real physical experiments. Well, let's do this first. Theoretical probability. If all outcomes are equally likely, and this is the only case in which we're going to calculate these things. If we have all outcomes equally likely, right, then the probability of an event E is just the number of outcomes in E divided by the size of the sample space. The total number of possible outcomes. And this is, of course, for a finite sample space in which all outcomes are equally likely. Okay, let's see. Let's do examples here. Okay, a bag holds 10 identical marbles numbered 1 through 10. 1 is drawn out. What's the probability you get marble number 5? Okay, all outcomes are equally likely here. All the marbles are identical, except for the numbers, I guess. There's only 1 outcome in the event get marble number 5. There are 10 outcomes altogether, so the probability is the probability of the number of outcomes in the event, which is 1, divided by the number of outcomes in the whole sample space. So it's 1/10. Second one, a fair die is rolled once. What's the probability you get an odd number? And this is all laid out here again. All outcomes are equally likely because this is a fair die. There are 3 outcomes in the event get an odd number, namely the outcomes 1, 3, and 5. 6 outcomes altogether, all equally likely, and so, probability you get an odd number is 3 out of 6, right? 1/2, and that should make sense, certainly. Half the numbers are odd. Okay, the probability of drawing an ace from a standard deck. In a standard deck, there are 52 cards. Drawing any card is just as likely as drawing any other, so the probability of all the outcomes here is the same. And there are 4 aces, so the probability here is 4 out of 52. This gives me a chance to say that you need to know the deck of cards. You need to know, you don't need to be an expert, but you need to know that there are 52 cards, that they're divided into 4 suits called spades, hearts, diamonds, and clubs, 13 cards in each suit, what the cards are, right? 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king, and ace. And so there would be 4 2s, 4 3s, all the way up to 4 aces. I need something to ask questions about that's a little more complicated than dice, but still not very complicated, so you need to know about the deck of cards. If you don't, like there's a picture in the book, and I advise you to go out and buy a deck of cards and play some cards, and you'll quickly learn it. All right, let's do another one of these theoretical probability things. This time we're going to roll 2 fair dice, 1 red and 1 green. Now if you roll 2 dice, and you can tell them apart, 1 red and 1 green, then you need to record as the outcome of the experiment of rolling 2 dice, you need to record what happened on the red and what happened on the green. So if you get a 3 on the red and a 4 on the green, you should record that as some sort of ordered pair. Right? So the ordered pair 3, 4 will mean 3 on the red, 4 on the green. Here are all the possible outcomes. Right? A 1 on the red and a 1 on the green, a 1 on the red and a 2 on the green, and so on. You can easily look that over and see that this is all of them. And there are 36 of these altogether, and that is because there are 6 for each die. What's the probability then of each of any one of these outcomes? Well, there are 36 outcomes altogether. They're all equally likely, and so each one has probability 1/36. What's the probability of the event containing these two ordered pairs right here? 5 on the red, 6 on the green, or 6 on the red, 5 on the green. There are 2 outcomes in that event, and there are 36 outcomes altogether, so the probability of that event is just 2 out of 36. I could have asked that same question by asking what's the probability of rolling an 11, right? Meaning a sum of 11 with 2 dice, because these are the only ways you can roll an 11. So the event roll an 11 would just contain these 2 outcomes. And that's the way you approach the next problem here. What's the probability of rolling a 9 with 2 dice? And that, of course, means a sum of 9. So the event E, let's call it, is the event that you roll a 9. What are the outcomes actually in that event? Well, you can roll a 3 on the red and a 6 on the green. You can roll a 4 and a 5 and a 4, or a 6 and a 3. And those are the only ways it can happen. The only way is you can get a 9. So the probability of E here, it's going to be the number of outcomes in E, which is 4, divided by the number of outcomes in the whole sample space, which is 36. Okay, let me say a few words about empirical probability. This is, as I was saying before, this is when you want to assign a probability to events, outcomes from an actual physical experiment. In order to do that, you need to be able to perform the experiment many times under very similar conditions. We're going to say identical conditions. And when you can do that, you can define the probability of an event E to be the number of times E occurred when you performed all those trials of the experiment over the number of observations, that is, the number of times the experiment was repeated. That is an empirical probability. It arises from actually performing the experiment and counting. Okay, here's an example. This table we can see shows the times at which Jill has gotten up on 10 different school mornings. Based on this data, what's the probability that she'll get up before 7:05 on any given school morning? So all we want, so the probability that she gets up before 7:05, it's going to be the number of times she got up before 7:05 divided by the total number of observations. So the total number of observations is clearly 10. And then we just have to go through and see how many of those times she got up before 7:05. That is, how many of those times this event occurred. So it's 1, 2, 3, 4, 5, 6. 6 times out of 10 she got up before 7:05. So we would say that based on this data, it's not much data, but we would say that based on this data, the probability that Jill gets up before 7:05 on a school morning is 6 out of 10. Okay, I want to say a few words here about a thing called the law of large numbers. And often abbreviated just LLN. The law of large numbers, not going to write much here, it's in the book of notes. Right? It says that the more times you repeat an experiment, the closer that the empirical probabilities will be to the theoretical probabilities. Right? That is what is really a fundamental thing, tying together empirical and theoretical probabilities, saying that theoretical probabilities, calculations made with math, are a good model for what actually happens in physical experiments. Okay, I also want to say a few words about a thing called, what some people call, subjective probability. And mostly we want to say something about this to distinguish it from the rest. Subjective probability, the classic example is the doctor says that John has a 60% chance of making it through the surgery. Well, what could the doctor possibly mean by that? He doesn't mean that he's just arbitrarily assigned 0.6 as the probability John will get through. Right? And it certainly doesn't mean that he's repeated the experiment of operating on John over and over and counted the number of times he lived. Right? So there really isn't any way he could get at a probability. What he actually means is that he's making an estimate based on cases he's seen before, patients who have some of the same characteristics as John and some of whom had different characteristics, papers he's read and what he's been able to figure out about when patients survive surgery, this particular surgery, based on that and so on. He gives John about a 60% chance. Right? It's a kind of empirical probability, but it's not really a measurement. It's more an informed guess used when there are just too many variables to make a decent estimate. All right, that's it for this lecture.